In this video, we'll do a definite integral example with a discontinuity. So we have this function f of x, which equals 3 if x is not equal to 1, and it's 7 if x equals 1, and I want to evaluate the integral from -4 to 5 of f of x dx. So let's begin by drawing a graph of this function. So I'll draw some axes, and our graph is going to be the constant 3 whenever x is not equal to 1. So I want to put 3 on the y-axis. We'll have this horizontal line because it's a constant everywhere except when x is 1. So that'll make this sort of thing happen. And because that's not happening when x is 1, we have to skip x equals 1. So we draw a hole there. Okay, and then at 7, when x equals 1, the output is 7. So I will draw a dot there, and the y value there is 7. Okay, so we are focusing on the interval from -4 to 5. So if I draw vertical lines at those endpoints of this interval, we are focusing on the area underneath this graph on the interval from -4 to 5. So if I were to try to shade in that area, we'd be shading in the stuff underneath this rectangle. Okay, so we should be shading all that in, but then when we get to this hole, if we evaluated this integral using, for example, a limit of Riemann sums, we'd split this up into rectangles, and if one of the rectangles had used 1 as one of the endpoints, we'd get sort of a sliver coming up here, like this, but when we let the number of rectangles go to infinity, that sliver would become infinitely thin. So instead of having like a rectangular shape like this, it would become infinitely thin. Okay, so we just have kind of like a sliver like that, and the area of just like one tiny sliver like this, well, that would just be 0. So all I'm left with is just the area of that rectangle. Okay, so what we end up getting is the integral from -4 to 5 of f of x dx equals the height of this rectangle is 3, and this base is 9. So multiplying those, we get 27. So the key thing that I want to observe about this is when we have a removable discontinuity like this, it will not affect the area as long as our function f is defined there. So because I had a point somewhere when x is 1, it gave me this like infinitely thin sliver of a finite height, and that has an area of 0, so it didn't affect the overall area of this thing. But what if our function was undefined at x equals 1? So if f is undefined at x equals 1, let's draw a picture of this graph. So we'd have our axes, and then we'd have, so our graph would be sort of this horizontal line going through 3, but at 1 we'd have this hole, and then it would continue onwards. But now there would just be no closed circle at 1, 7, because our function we're assuming now is undefined at x equals 1. So if we focus in on our interval from where x is -4 to where x is 5, and we talk about the integral from -4 to 5 of this new function, let me write it in purple, f of x dx, this is what's called an improper integral. So it's an improper integral because there's some value of x for which this function is undefined in the interval in between -4 and 5. So right now we don't know how to handle these. You would see these in the next calculus course in Math 1B. All right, so let me just put a little bubble around all of this. So this completes our last goal for this section. Over the last 2 videos, we've talked about how to apply our definite integral properties.